Is it audible?
Yes, sir.
Am I audible?
Yes, sir.
Okay. In this class, we'll discuss about all the instructions which are supported by the ARM. In the last few classes, we have discussed about how to develop the programs using the assembly, using the compare, the flag affecting instructions, and also we have learned about how to implement if and else, how to implement the loops, using the compare instructions and other instructions. We also learned about how to implement the procedures. So we have written few programs to implement the different algorithms. So now this class and next class, we will learn about all the instructions, how they work, and so that based on the requirement, you can able to use those instructions in algorithm implementation. As I was telling that all the instructions of ARM are classified into data manipulation or data processing instructions. Then you have a branch instructions. Then you have a load and store instructions. Then the miscellaneous. These are the four groups are there. The majority of the instructions are present in the data processing group. So data processing instructions, basically there are four groups are there in that. The first one is a data movement that we have studied what is called move instruction. Today we will learn about what is MVN. Then we have an arithmetic instructions where we have studied about add, ADC, and the sub. We also look into today the instruction called SBC, RSB, and RSC instructions to support implementation of logical operators like an and or in implementing the algorithms. It also provides logical instruction called and or, but also to implement the bit and or, the bit and operation, or operation, XOR operation. For the bit implementation, these are required, and or, XOR, and BIC. This is for bit manipulation, what we have in the C language. No, similarly, you can implement in the using these logical instructions. And we already use the CMP instruction. The other variation of CMP instruction is CMN. And also, so there are other comparison instructions which are called test and test equality, which are used for affecting the flags, not for generating any output operand. We will see that how they are used in the logical implementations. If you look at any instruction, as we were referring the instructions in the memory, all the instructions in ARM takes 32 bits. Totally 32 bits will be there. If I write instruction called move or add, how these 32 bits are occupied? What are the contents of this 32 bits? So these 32 bits, whatever I'm referring it, is nothing but represent any of these instructions. All these instructions are represented with the same format. If you take, let's say, add instruction will have a 3 operands. Most of the instructions will have a 3 operands. So 3 operands means, so one is a operand 1, that is Rn, indicated by Rn. The second is operand 2. And once you perform an operation like an add, subtraction, or AND operation, you have to store the result in another register. So that is a third operand. There's a destination operand. That means that every operation you perform among these instructions will require basically, so 3 registers or 3 operands are required. So first is operand 1, we call as an Rn. Then it's called as an operand 2. Then the destination operand where you keep your answer is called as Rd. So we know that there are 16 registers are there. So 4 bits are required to represent any of the registers. So that's why 12, 13, 14, 15, 4 bits are given for this, 4 bits are given for this one. So 2 to the power of 4, 16, any of the register, I can represent this in this space. Now, also we know that there are so many instructions are there. That means that this format I'm using to represent all these instructions. How do I know that which instruction this is representing now? That depends upon the opcode. So how many bits are there opcode? 5 bits are there, 21, 22, 20, 21, 22, 23, 24. So 4 bits are there, 1, 2, 3, 4. 4 bits are there. So these 4 bits, 2 to the power 4, 16 combination you can able to represent. So look at that. How many are there? There are 16 combinations are there. So which combination this instruction represents depends upon what you write here. Depends upon the instruction you write. So these 4 bits will be represented by an assembler, will be chosen by the assembler based on what instruction you're going to write it. This is an about opcode. There is a 1 bit is represented, allocated in the 32 bits, that says that whether after the execution of the instruction you want to affect the flags or not. S suffix. So if you use an S suffix, this bit will be set to 1. Otherwise, this bit by default will be 0. Now, almost all the instructions, whatever you use in the in this data processing, are all conditional execution enabled instruction. In the sense, you can make the instruction execute based on a condition or not do anything based on the condition. So you can attach a condition code for any of this instruction. So what are the condition codes? Equal, not equal, greater than, less than. These are the condition codes. How many bits they are provided for the condition codes? 28, 29, 30, 31. 4 bits are provided. That means that there are totally 2 to the power 4, 16 condition codes are existing. These condition code we studied in the in the program. So I'll just show you the condition codes before we move. So these are the condition codes what we have studied. So equal, not equal, higher or same. So I said some of them are used for signed numbers, some of them used for an unsigned number. Effectively, all these condition codes at work based on 4 flags only. You have only 4 flags, either 0 flag, carry flag, sign flag, overflow flag, or combination of what? Carry and 0, and so combination of sign flag and the overflow flag. So for sign numbers, we use what is called sign flag, overflow flag, and the 0 flag. For unsigned numbers, we use what is called as carry flag and 0 flag to find out less than or equality conditions. And the remaining are directly. For example, 0 flag is there, equality. So totally effective, there are 16 conditional codes are available. You can use based on your requirement. Except, so if there is no condition you return, it is by default called AL. AL means always. That means that the instruction is going to execute always. No condition is there. But we don't require to write AL. Even if you write AL, nothing wrong. But we don't write AL if there is no condition is there. By default, that means that, so AL is taken. So there are 15 different conditions you can able to implement on the execution of instructions. So it is very important. You should able to refer all these things, understand the meaning of the left side, that is a suffix, and also the what flags are used. You should able to remember, practice at least 2-3 times this one. So only confusion here in this area, you should able to very clear that for sign numbers, we use sign flag, n, overflow flag, and the zero flag if less than or equality condition is there. If there is no equality condition is there, we use only what flag? Sign flag and overflow flags is only used. So similarly, in case of unsigned numbers, if I'm looking for greater than and less than, I'm using only the carry flag. If I'm using for greater than, less than, and with an equality, I'll be using what is called carry flag and a zero flag. So similarly here, even the sign numbers, if I use for a equality also along with a greater than, less than, I'll be using a zero flag. So for unsigned numbers, I'll repeat, for unsigned numbers, I'll be always using what flag? Carry flag and zero flag. For signed numbers, I'll be always using what flag? Sign flag, overflow flag, and the zero flag if the equality condition is required. So zero, sign, overflow flag are used for signed numbers to implement the logics for the signed numbers. For unsigned numbers, we'll be using always carry flag and the zero flag. So this you should remember in your mind, and you should be able to try out these options on a program to compute the smallest and largest of a 32-bit number. In that program, you should try out and understand the meaning of all these flags. Now, as I said, so coming back to here, I said there are 4 bits allocated for a condition code. If no condition is there in the instruction, for example, add, no condition is there, means it is AL condition always. AL means all bits are 1, 1, 1, 1. Now, so we have understood that now each 32-bit instruction, that is a 32-bit number which is represents an instruction, has the space for opcode, meaning of the instruction, has a 1-bit space to indicate the flags to be affected or not, has got a 4-bit space to indicate it's a conditional code instruction or not, and also it has got a space for indicating the 3 operands, operand 1, operand 2, plus the destination operand. Now we will see the other possibilities. What are the other possibilities? Whenever I used add instruction, move instruction, and even a compare instruction, many times I compare with a number. So if you remember, if I say move R0 comma hash 2, I can use a number. Even in case of an add R1 comma hash 30. So at the same time, add I can also use what? Add R1 comma R2. Sometimes I use one of the operand as a number. Sometimes I use one of the operand as register. That this is that operand 2. So that means that operand 2, sometimes I use a register for this. Sometimes if I have a number with me, I use the number as an operand. So operand 2 can be 2 possibilities. Either it can be what? It can be an immediate number, or operand 2 can be what? It can be a register also. How does the instruction knows that you should treat this operand 2, that is whatever you encode here, it should be a register or a number? For that, they have provided 1 bit called L bit, literal 0, that is 25th bit. So this bit says that whenever 0 is there in this bit position, that means that this is a register. That means that you have the numbers in the registers, you are performing the operation on the register data. Whenever the L, this bit is 1, that means that, so one of the operand is a number. It's a part of the instruction. You are writing a number inside the instruction. Now the question comes. Most of the times, the number, whatever we refer, correct now, is a number we were using all these days. I was telling you that you cannot write number whatever you write in the move instruction. So for example, if you take the here one instruction, if I write it, see move, so R0 comma hash 8, it works without any confusion. Okay, now let's say I'm going to use 2500. Let's see it works or not. I don't know. It depends upon the numbers. So there's an error is there. That means that what? Whatever the number you write here may not work here. Yes or no? So why this problem is there? Because the operand 2, the space, you see, the number what is we write in a program, that is, for example, I want to load a number into R0. What is the size of an R0? 32-bit. That means that 32-bit means 0 to 2 to the power of 32 minus 1. That much of combination should be possible. whatever I inherit 2500 is a valid number, but it's not allowed because the 32-bit number you're using to represent an instruction should provide is providing only how many bits? 0 to 11. That is only 12 bits is providing to represent operand 2. So whenever the operand 2 you're using to represent a number, not the complete 32 bits you can use to represent a number, because we know that all the instructions is what? One word instruction. Word means what in our architecture? Word means 32-bit number. So one complete word I cannot use to represent a number, because why? The instruction should also represent so many other things. Only it provides how much? Only it provides 12 bits to represent your number, which is a part of the total instruction. So in this 12 bits also, there is a method is just to store it. In this 12 bits, they provide only 8 bits to represent a number and remaining 4 bits to shift that number and allocate. We will learn that later. So effectively, only in the 12 bits, 8 bits available to represent an immediate number. That is why whenever you use a move instruction, don't think that any 32-bit number I can able to represent. No, not possible. Only they provided 12 bits. In that, only 8 bits is possible. That 8 bits you can rotate and arrange it in the 32 bits. And that is what the next 4 bits provides. We will see that how immediate operands, what immediate operands can be represented here. So these are one limitation you should be able to understand in a ARM. Immediate number means it's not all the numbers possible. Only few sets of numbers are possible because they are provided only 12 bits to represent the 32-bit number. Now, so whenever you're using this as a register, that is operand 2, I'm not using as an immediate. If I use that as a register, there is a provision is there. This is because operand 2. So we know that the operand 2 comes through a barrel shifter in case of an ARM architecture. That means that whatever the operand 2 you specify, that means that operand 2 is what? When I'm talking about a register, I said operand 2 can be what? Either register or it can be an immediate. Now I'm thinking of a case of a operand 2 is a register. Whenever operand 2 is a register, you can make it to pass through a barrel shifter and able to make it work. See, so whenever it's an operand 2 is a register, what are the possibilities is there? You can shift the number whatever you have in a register by using a barrel shifter and then supply the number to the ALU. We have used this in our programs. Now, so today we will study about what all the operations barrel shifter provides for me and what is the size of rotation I can able to implement using a barrel shifter. As it says already here, the shift value can be either be what? Shift or rotate value can be either be 5-byte unsigned integer specified in bottom byte of another register. Both our possibilities are there. We will see that how it will be implemented within examples. Now we will start with one by one instructions and what are the barrel shifter operations. Those instructions we will see that first. Now, now I'm going to work move. Let's say R0 hash. Let's say 1. I'll give it hash 1. Now R0 will be moved into the 1. Now, so am I audible?
Yes, sir.
So now I'm introducing the first new instruction for today's class, MBN. MBN means move to the destination register, whatever the, let's say I'll take R0 itself, move to the destination register after negating the source register, source operand. Now what is the source operand? R0. So there are two operands are there. This is a destination operand. This is my source operand. It can be a number also. It can be a number also. I can write directly 1 here. Directly I can write also. So what this instruction MBN says? That means that MBN says that move into the R0 register after negating the contents of R0. How does it work? Let's understand with an example here. So look at here for a moment. Now what I have done here. So I will just maximize. I have written the operations with clearly indicating what will happen. So now 001 is there in the R0. I will split the 001 as what? As a bit pattern. 00, 000. The last digit is what? The 1. That is why 001. That is hexadecimal. I converted into binary pattern. Now, whenever I say n, that means that negate the number. So I'm negating this number. What is the negation number? Wherever 0 is there, make it 1. Wherever 1 is there, make it 0. So I negated all the bits. Look at this. I have negated all the bits. So here it's a 001 was there, the 110. Now, after with a negation, what is the value you get? So look at that. That is if you write F, then F, 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 and FE. This is the answer is supposed to get it. Now, look at this program. Now this is the value I have loaded here. Now I am writing this instruction. I'll compile this program, see that whether my answer is correct or not. Now I'll run this program. Now 0, look at this value, R0 is 0, 1. Now I'll execute this instruction. My expected value is what? FFFFE. Just see that. So I got FFFFE. That means that this is how MBN instruction works. Whenever you want to negate a number, directly you can write a number also here, or you want to negate a number which is there in a register, you can use always this one. For example, if the question is asked in the Viva or quiz, so write a program to complement a number. It's a very simple, one's complement of a number. You can just use one single instruction and you can complement a number. If the question is asked to find out a 2's complement of a number, it's very simple. So just do the MBN instruction and add to the register number 1. So 2's complement is nothing but adding 1 to the 1's complement, so that we can able to implement a programs like that. So keep in mind, there's 2 possibilities to find out a 1's complement and a 2's complement of a number using a MBN instruction. Now we will go to what is called as, so as I said, the different operations called the shift operations, what is possible here. Now I'll be learning about the different logical operations, logical in the sense, the shifting and the rotation operations possible with what is called as, so the barrel shifter. We will learn one by one. We will go with the logical left shift, since already we know that. Anyway, I'll just, for the sake of clarity, I'll just complete that one and then we will learn it. So we will start with an LSL now. Now, how does the LSL instruction is going to work? Now, I will introduce now move, move R1, R0. R0 is already, if he is there. So, and then I'll say LSL and then #1. So this is the format of using the instruction whenever you want the operand 2 to be passed to the barrel shift. Which is operand 2 here? This is operand 2. So this is operand 1 and also this will be the destination operand. So now when I say LSL, you are logically shifting the number what is there in the R0, so by 1. So if you look at that operation, whatever I've written that operation. So just steps, you look at that here. So now what I have done, I have loaded in the already FFFE, because why? I already number shifted. If you look at this here in this program, already I have performed MBN. So what is the number I have? So I'll compile this program. So you can just look at this. The number whatever I have with me is already. So I will execute this instruction. See that number whatever I have with me already FFFE. This is the number what I have in the R0. Now I am shifting it left by 1. So when I shift it left by 1, now first I have written the number. I have written the number in the binary format FFFE. So split every digit into its binary pattern, write the 32-bit number. Now I am shifting it left by 1 bit. So whenever I shift this number left by 1 bit, 2 things you have to observe it. Number 1, all these shift operations, whatever we study, it influences a carry flag. The carry flag value will going to change. Even though you are not written the S in the instruction, S is not written in the instruction. For example, now whatever the move instruction I've used, even though S is not there, the flag is affected. What flag? Only the carry flag. Whenever you use a barrel shifter, the carry flag is affected. Look at here, it's changed here. So look at here, it is changed here. Look at here, it's changed here. Look at it's changed here. So everywhere, that means that any of these operations you perform using a barrel shifter, one flag is going to change always, even though you do not specify the yes. That is called as a carry flag. So in case of a logical left shift, what will happen? Whenever you shift this number of vacant position you're creating on the right side will be always filled with the zeros. And each time you shift out a number, the number which is shift out will be entered into the carry flag. Since I am shifting only 1 bit, whatever the bit I'll shift, it will enter into the carry flag. So look at this combination what I've written. So this is the number I have it. Now I am performing what me shift. I am performing only 1 shift to the left. So the whole number I shifted left. Now the whole number whatever I have shifted left. When I shifted left, what will happen? 1 bit which is coming out will enter into what? The carry flag. And the 1 vacant position will be filled with what? 0. Will be filled with a 0. Now the new number will be what? FFFC. This is the new number. Whenever you shift left, it's also equivalent to what? It's a multiplication by 2. That we have seen that. You can check in the calculator. Now going back to my program. If I execute, this value should become what? R1 should be what? C should be able to get it. I'll execute this instruction. So see that FFFC, you got it. So this how you can able to implement this one. Now we will take another case, another version of specifying the shifter operand now. Now what I'll do is, now I will load into the number. I will load into the R0 a number. So let's say hash 000008. Let's say I've taken some number. Now I want to shift it left by 3 times, logical shift. So I'll say I'll use another register. Instead of a number, I'll do a register, so that variable is used to represent the number of shifts. Hash 3, I've used it now. Now I change this instruction little more. R0 have a number, but instead of number 1, I specify the R3. That means that there are 2 possibilities there. One is you can shift a number to the left by indicating the number directly using a hash number. The other possibility is what? You can indicate the amount of shift a number has to perform, that is R0, how much shift is indicated by a register. Also, you can be able to indicate it. So this is using a variable to indicate the amount of shift, either to the left or to the right. Now we will see what will happen now. I'll compile this program. So we will see that, and we will see that how we can able to calculate that. So now I will finish. Now I will stop at this point. Now see that R0 contains how much? 8 is contained here. R3 contains how much? 3 is contained here. Now I have to perform and to find out an answer. So look at this calculation for a moment now. So okay. So now I am performing this operation. Look at this operation. Now I've taken 8. So I've written the 08. I produce a binary pattern for that. What is the binary pattern for that? So 0, 0, 0, then 0, 0. This is the 8. So that's why 1, 0, 0 I written. Now I taken this number, whatever the number, I just shifted that left by 3 bits. See that? See that? So what I have taken in the cursor, you can keep it like that. First you can keep it back like that. Then shift the number 1, 2, and then 3. I've shifted the number. When I shifted the number, you can see that the 3 vacant positions are created here. So what you have to do in the vacant position, you have to fill with always what? 0, 0. So I filled all the 3 positions with what? 0, 0, 0. So whenever you shift out, the last bit, what is shift out? This is my last bit. So the last bit which is shift out will enter into the carry flag. Now, after you perform this one, this is the number, I have got it. Now, I will arrange the number, correct now, and I have arranged the number, and then I'm writing the answer 0. So 0, 0, 0, 0, 0. The 0, 1, 0 is what? 4, and then 0. This is my answer, I got it. So this is how I will prepare my answers once the number is given. First, you have to take the number, split in binary pattern, shift it how many times it's required. Last shift you put into the carry flag. The vacant portion filled with the zeros. Then whatever the number you get, 32-bit number from the right side. From the right side, 32-bit number. Don't take the shifted numbers. From the right side, take the 32-bit numbers. Then convert into an hexadecimal value. So this will be your answer. Now we'll go back to the program. We will see that now what is the value should be there in R1. Now R1 should contain what? 40 should be there. So now I'll execute. So now you got a 40. That means that my calculation and what the result I got will be the same thing. So this how you have to given any number in the quiz, you should be able to find out without the calculator like this one you do, because in final exam, so when it's a offline, you will not be having the system calculator and everything. Of course, you can use a normal calculator and hex and everything. But if we ask the question that to show the calculations, you should be in a position to show the calculation. So better to practice with your pen and paper so that you will be able to understand whether your answers are correct or not, and also principles you will appreciate. Am I audible?
So I have one doubt.
Yeah.
So if we shift the left, like when we shift it by 3, which bit will be stored in the carry flag?
Last bit shift out. Last shift out.
Okay.
So for example, the first shifting is 0. Second shift bit is what? 0. Third shift is what? Last bit is what? 0. That will be stored in the carry. Actually, every bit will go to the carry flag only, but the last bit will remain. That will be the one which will be there for you.
Thank you, sir.
Now, in this program, you should be able to understand that the maximum value I can use for a shifting a number. That is, what is the value maximum I can represent here in the LSL or something. So this, as I said already, so whenever you refer the instruction, so this operand 2, which contains the information about the register also and the shifter operand also. So that means that you can see that 5 bits are allocated to indicate the amount of shift. 5 bit means what? 2 to the power of 5. That is 32. That means 32 means 0 to 31. So if I write any number here in the program, if I write any number, for example, if I write here, so R3, so let's say 32, and if the assembler is proper, it should not allow, it should give me an error. So in this case, it is giving because it is an indirect operand. The runtime, there's an issue is there. Let's say if I am using this directly, so hash 32, so it should be able to give me an error. See, it gives an error saying that what? So shift operation out of range. So what is the allowable range? Only 0 to 31 is the range. So this you should be very clear. If you give 32, you should see it's an error in the instruction. It is not a executable. So because that is why the allowed is available. That is a amount. 5-bit unsigned integer is allowed to represent the amount of shift. Now, so we have understood now the logical left shift. Similarly, you can do logical shift right. So whenever we shift right, you can just try out in your system the same thing, same method, you can use it. What are the things you have to understand in the shift right? You are just shifting in the right direction. So use your the cursor to shift it how many bits. Whatever the vacant portions created on the left side, fill with the zeros. Whatever the bit which is shift to the last bit, which is shift out from the right side, that you put into the carry flag. That is called as a logical shift right. This is called as division by a power of 2. So this is called as LSR, logical shift right. So this is logical shift right is nothing but a division by a power of 2. So you can take some number. So today I'm just sharing an assignment after the class. So each one of you solve that assignment, put into your folders, USN lab folders. So in this assignment, I'll be giving all the shift operations you perform manually in the paper and able to write it and put it today only. So we have understood logical shift left and the shift right. Now think about a signed number. Think about a signed number. So what is a signed number? Any signed number, for example, if I write -1, how does the signed numbers will be represented? Signed numbers will be represented for, if the minus means is 1, because why? So 1 is the bit number 32, the bit number, so 31. So then it goes, and then it's the last bit 0. So the remaining bits, whatever there, will be used to represent your magnitude. Now in this case, what is the magnitude of 1? Because 2's complement will be represented. 1 means what? So 1 means, so it will be 0, 0, 0, 0, 0, 0, 0, 0, 0. So 16, 0, 0, and then 0, 1. Just see that. So I've used, okay. Now since it's a -1, the magnitude I have taken first. So what I have done, so since it's a -1, since a minus, I placed 31 bit as a -1, I have placed it. Now what to be placed in from 30 to 0, that is magnitude, I'm calculating it. So I've just taken 1 from the number, I've just split in the binary. Now I'll take a 1's complement of this one. So I will do 1's complement. So I'll do 1's complement. So how do I do a 1's complement? So I will do the inversion of all the numbers, whatever I have it now here. So 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So, and then 1, 1, 0. That means that I done a 1's complement. Now what I have to do? I have to do a 2's complement of this one. I have to calculate 2's complement, because so signed numbers are always represented in 2's complement. The magnitude is represented 2's complement. So when I add a 2's complement, see that 1 plus 1, 1 plus 0 is what? 1. All the remaining 1, 1. That means that, so I have to perform basically what? I have to perform addition of 1 to the 1's complement number. So now, so after I do this one, so what I'll get? So first I have taken the 1's complement, then added. So to get the 2's complement, so I have to do 1, 1, 1, 1, 1, 1. Okay, so now what I've done for 2's complement, so add 1. So that's what I did it there. Okay, so now this is the 2's complement. Whatever the number I have, it is a 2's complement. It is a 2's complement. It's a 2's complement number. Okay. So look at that. Now this number in a hexadecimal way, if I represent it, it's nothing but what? So this is a number. Now we will see that how the numbers are represented in 2's complement, and we will go to the other logics now. So now I'll go to the program. So I'll remove everything. I'll just say move move R0 equals hash -1 I specify. So I'll compile my program. I'm starting using now negative numbers in my programs. So whenever I say -1, that is nothing but I said you are representing -1 in what format? In R0. You're storing -1 in R0. What is the way it stores? Whatever the way I shown it. That means that, so if you look at this, whatever the combination you have here, yes or no, the last bit, except last bit, I'll leave the last bit. Actually, there is no meaning in taking the last bit actually in all these things, because you're representing the magnitude is 32 bits. So there's no meaning in taking the last bit. It's not required. So now this, whatever the value I have, correct now. So whatever the value I have, that is 30 bits. I will take that 31 bits, including 0. So I'll take it. I'll put this bits here. I'll put those bits here. Because why? This is a sign bit. So this is a sign bit. So now I'll add the sign bit. I will take the sign bit. That is a 1. So this bit is nothing but, so sign bit for me. I'll just take a sign. Remaining bits, I'm just copying it now. So copy. So now this becomes this value. Now this becomes this value, whatever the value I have taken. So how do we do it? So first, if take a sign is there, represent in the 31 bit, whatever the sign. Negative means 1, positive means 0. Now take the magnitude, represent in the binary pattern. Now takes the 1's complement of that, add 1 to find out the 2's complement of that. That is how many bits are there? 31 bits are there. Now take the sign bit, whatever there in the 31 bit, that is as it is. Now remaining is a magnitude. Remaining is a magnitude you're taking it. So now once all the bits, 32 bits are ready, you represent them in a hexadecimal. This is a value you're supposed to get it. Now, so same thing, I'm just running it here. Now when I run this program, I supposed to get FFFF in the R0 register, because automatically negative numbers are represented in the 2's complement representation. So see that FFF, you got it. So this is how you should be able to write in the quiz. In the quiz, we may give an instruction like that. We will ask you what is the value of an R0. Then how do you do it? So you have to follow the same method, whatever I followed, so that you should be able to find out, so what is the value you're going to get for in the R0 register. Always remember that whenever negative number is inquired in your program, you will be representing the negative number in the 2's complement representation. Always remember that one. Now, so now I have understood that how it will be represented negative numbers here. So going back to the discussion here only. So whenever you are using unsigned numbers, logical shift left or logical shift right, it works fine, because in unsigned numbers, there is no question of sign flag will be there. You can shift left or right, nothing will happen because there is no sign flag there. The same logical left shift and right shift operation always have an issue when you are doing with signed numbers. Let us take a first side number. If I am taking a logical shift right, when you're taking a logical shift right, let's say you're taking a sign number, the last bit will be representing a sign. When you shift the number to the right, then what will happen? The sign bit has moved to the right. Whenever sign bit has moved to the right, you are copying the 0 here always. Whether it's a negative number or positive number, you are always copying 0. That will not work well. See, if it's a negative number, you are required to copy what? 1. If it's a positive number, you're required to copy the 0 in the empty position. So that is where logical shift right fails when you are using assigned numbers. In such cases, most of the assembly, almost all the microcontrollers provide an instruction called arithmetic shift. Arithmetic and the logical shift. The meaning is what? In both the cases, shifting happens. But in case of an arithmetic shift, it is used to handle the signed numbers. If logical shift means it is used to handle the unsigned number. L means unsigned number. A means it is a same shifting operation, signed numbers. So look at that. Now what has happened here? Now whenever you shift the arithmetic signed numbers, whenever you create a vacant position, what will happen? The last bit, what was there, it is same thing is used to fill the empty space. It is not the 0 is filled. See that 0 is coming out from here. Now it's what is there here? whatever the last bit was there, if it is a signed number, it's a negative number, 1 is there, the empty portion will be filled by the 1 only. It's a positive number, it will be filled with 0. That means that for positive number, 0 is filled. For a negative number, what is filled? The signed number, that is whatever the 1 is filled. That is why my answer will be the perfect. Let's take an example now. Now already we know that -1. So we will go to the program. So now I have taken a -1. So -1 is represented like this one. Now I'll shift this number using both right side. So using logical and a arithmetic shift. You can understand what is the difference it makes. Now I'll shift it, this move R0, whatever there R0. Now logical shift right, LSR. So LSR #1, I'll do shift it now. Now what we'll do, whatever the number -1 means what? FFF. So when you shift it right, then what will be produced? Because you are creating one vacant portion, 1 will be shifted right. So this is the number you're supposed to get it. 111. So 111. 1, and it continues. It continues until the 1. So let's see that what is the value you're going to get it. So I'll execute this program. Now, so look at the value now here. So you got FFF. Since I'm using a logical shift right, look at the value there. The 1 bit which is shifted to the right will be filled with a 0. See that now? So what is this value? It is nothing but what? 011 is nothing but what? 7. 7 FFFF is produced. That means that you have got a -1. You got a -1. When you shift it to the right, you got a positive number. That means that not expected result, because minus number has to, whatever the negative number has to retain the sign. When I'm shifting, my intention is what? Shifting the magnitude. My intention is not shifting the sign. So when I shift it to the right, my intention is shifting the magnitude, not to the sign. So now I'll use an arithmetic shift now. I'll use my arithmetic shift now. Now if I use an arithmetic shift now, so I will comment this line now. So move R0, 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 ASR, arithmetic shift right, with a #1. Now I will compile my program. Now what is the last bit? The last bit is 1, sign. So when you shift it right, one vacant portion is created. The vacant portion should be filled with what? Whatever there at the sign bit before the shifting. Before shifting, what was there? 1 was there. Same 1 will be copied now. So look at here now. So I'll execute. FFF is there. Now when you vacant portion is created now, what is the value? Since the vacant portion will see, you are shifting the number 1111, it continues 111. There's a 1 vacant position here. What to be filled here? Whatever earlier was there. What was earlier was there. So earlier was what? 11111 there. So that means that what is here in this position, that is the sign bit. The same thing will be filled in the vacant portion. So it will be filled with what? 1. So that means that, so when I perform this operation, the vacant portion will be filled with the sign bit of the number previously, whatever there is there, so that you will get the same thing. So, and you're shifting right. So look at that, what you have here. So when you shift, when you execute this one, what is the same number? So -1 you had, that is a -1 FF was there. The same is there, because why? It will be filled with the same thing only. So this is how negative numbers are handled whenever you use an arithmetic shift. So number sign will not be changed. So this is the meaning of arithmetic right shift and arithmetic logical shift right. So only thing is it's used for unsigned numbers, it's used for a signed numbers. So whenever you use a signed numbers, you manipulate them, you don't want to lose the sign of a number. That is why we use the sign of a number like this. So now, so you can take a -4, try to shift it, you will get a -2 only, -2 only. Since you have taken a -1, when you shift it, -1 only you'll be getting. So if you take -8, you take it. Try to divide, try to shift it by right by 1 bit, you'll get a -4. Again, take a -4, shift it right, you'll get a -2. That means that your answers of a negative numbers, shift it right, you'll get a perfect division only, you'll be getting it. Yes or no? If you use a logical shift, your answer will be wrong, you'll get a positive number. So that is why when you use a signed number, you want to produce a division effect, you have to use what is called as shift right, you have to use it. Now, we'll come to the last two operations, that is a rotate and the rotate right extended. So what is a rotate right operation? You may ask the question, sir, ASR is there, why ASL is not provided? See, look at what is the meaning of a logical left shift. When you shift left, the carry is lost. When you shift left, carry is lost. Even in case of arithmetic operation also, if they would have provided, the carry, the sign flag is lost. That is why There is no meaning. When you shift left, sign flag is always lost. That means that you're not filling the sign flag, you're lost. So that is why logical left shift is the same instruction used both for signed numbers and for unsigned numbers. Only when you shift it right, the sign position has to be filled. That is why we use a different. So for the left shift, use the same instruction for both the signed and unsigned numbers. For a signed number, only for the right shift, you have to have a two instructions separately is available. Now we have learned the four instructions for shifting to the left and right for the signed and unsigned numbers. So let's finish in the 5 minutes. We will do the rotation operation. Am I audible? Am I audible?
Yes, sir.
Yes, sir.
Okay. Now two types of rotations available in the assembly in the microcontrollers. Number one. So let's consider the rotation right. I've considered it. There is only right rotation is provided. Left can be used with using a right instruction only. We can use a certain logic in the program. We can do it. So two types of rotation is available here. One is called rotation not through carry. Other is called as rotation through the carry. In rotation not through the carry, what we do, let's say right rotation. Whenever you rotate a number using ROR, like a LSL, you use an ROR, you give a number, #2, #3, or in a register, you can specify. When you rotate a number, what will happen? The bit which comes out will enter into the empty position here. It's a rotation. See that here what will happen? You're losing the bits. You're losing the bits and filling with the zeros. Here you're not losing the bits. You're rotating it. Whatever the bit which comes out will enter back into the empty position. So this is called rotation. But what will happen is whenever you're rotating it, the bit which goes out also enter into the carry flag. So the last bit, whatever you're rotating out, will enter into the carry flag. This is called rotate right. Now, let's understand what is called rotation through the carry. Here, the effective size of a number is what? 32 bits. Here, effective size is what? 33. Because why? 32 bits of the register, whatever you're rotating, plus one carry bit is called, that is also part of the rotation. Now, what will happen? 32 plus 33. 33 bits effectively rotating it. That means that carry bit is inside the circle. Look at that. Your carry bit is inside the circle. Here, what? Carry bit is outside the circle. Now, whenever you rotate through the carry, whatever the bit which comes out will enter into the carry flag. What is there in the carry flag will come out into the empty vacant position. That means that you should include that 33-bit rotation is possible. So carry flag is a part of the rotation. So whenever you do this one, for rotation of a number, reversing of a number, for finding out polynomials, so many logics which you take a lot of programming in the C language, you can implement in a few instructions in assembly. So because of this operations, this is a beautiful operation. If you want to count number of ones in a given number, it's very simple. You rotate it, check the carry flag. Even you can do with a shift also. So how many ones are there in a number? How do you do it in a C language? It takes a lot of programming. That is, you have to use masking and everything. Yes, because you do not have an access to the carry flag in a C language. When you write a program in a C language, I will ask you to how to count number of ones in a given number. There is no carry flag is there. You cannot access it. What you have to do is you have to use a masking. You have to shift it. You have to shift it and find out the mask. You have to AND it. So many operations you have to do it. The beauty of the assembly language programming is what you can do the bit manipulation. That is at the very low level you can access it. You can access the carry flag. Provision to access the carry flag by a programmer makes your so many algorithms very simple. So that is why some of the times, some of the very low level programs which is required to execute many number times in a day, we people write in assembly only because the amount of instructions you require to implement that logics is what is very small number of set of instructions required. So one example is a carry flag. You cannot access the carry flag in a high level language, whereas in low level language I can access the carry flag so that polynomial, palindrome, number of bits checking, number of zeros checking, all those things I can do using a carry flag. So these are the two instructions available here. Whenever you want to rotate to the left, what we have to do is use ROR, but use 32 minus the number. For example, I want to rotate left 2 bits. What I have to use? Use the rotate right only. What you have to write? 32 minus 2, you do it. So same ROR instruction, I can use it, ROR and RS instruction for performing the rotate left. But what I have to do is, whatever the number you want to rotate to the left, that number you subtract from a 32. Then it becomes a rotate left operation only. You can just go through once, you can try out, you will get it. So this completes all the rotation, that is whatever the possible through a barrel shifter, the shifting rotation, we have completed it. I request you to go through the instruction, take some numbers and perform it. I'll send today through email one assignment. Please write it and put it in the USN numbers of all of your whatever I created in the drive.
So when should we submit it?
Today night only. I want you prepare for your quiz. Yes or no? So I want you to
Yes, sir.
prepare for a quiz so that every day